Another keynote speaker from Russia, Ivan Oseledets, is going to talk about the successes and problems of LLMs, where they increase the speed of coding and analytics, and where they experience barriers. A round of applause, and we're going to learn that very soon. The Doctor of Physical and Mathematical Sciences, Professor of the Russian Academy of Sciences, General Director of the AIRI Institute, Dean of the Faculty, Dean of Artificial Intelligence Department at Lomonosov Moscow State University, Ivan Oseledets, with the report Successes and Problems of LLMs. Good morning, everyone. On the one hand, I'm going to talk about the success stories. There will be some announcements from our institute. In the end, I'm going to go through some problems and what problems are we addressing, try to address, and what results and outcomes our efforts provided us with. 93 articles with A* conferences, so pretty good results. So that's more than any other centers who are engaged in this effort, which is good. But I mean, articles is not written for the articles' sake. We have quite a lot of practical applications, implementations, integrations in healthcare. And I think 30 speakers on this conference with their reports and presentations. So it's not only my presentation that is going to talk about that. We can walk a lot around the exhibition and see our results and applications. There was an interview of Andrei Karpaty, 1.5-hour interview. And it's great. And don't use summarization for that in ChatGPT or any other Telegram channel summarization of this interview, because it is really exciting. The topic that was not very evident for me and that I got really interested in is, sometimes the people say that LLMs, they just remember. We say that usually it works like that. We pre-train the model, we upload the data from the internet, we train the model, and the general public understood that, but some did not get it correctly, and they start, now we see the messages that, okay, look, an LLM can be trained on Reddit and Wikipedia. How can it be an artificial intelligence? It just remembers some trash and just regurgitates it in your search results. And yes, we can hear that opinion. And after we have explained how it works, we have to explain to the general public that they got it wrong. The LLM uploads a huge number of text. If we just talk about the text, that's text, okay, but hundreds or 300 of terabytes, because that might include videos and images. But if you look at large language models that are being published right now, there are models with trillions of parameters. The GigaChat, the flagship model, is 70 billion parameters. So the entire world is more of a 20, 30, 70 billions. There are some models that are a bit overflown with hundreds of billions of parameters, but you give them 300 trillion tokens, and you have 20 billion parameters at the output. So that's a very noisy selection and a very good compression. So if you take a piece of pre-training, even after cleaning it, you won't be able to understand how these models are trained. But basically what they're doing is that they do this absolutely outstanding compression effort. And if we talk about the main success story, it's that the community and the researchers as well as companies understood that now we know how to scale it. How do we improve the quality of these models on a system-wide basis? We get more data, we clean data, we label data, we launch new trainings, we get some new hardware. For that, we do it in a more efficient manner. There are new algorithms that appear. I'm going to talk about that later. So it's a kind of an iterative development, but we're talking about the scale of one architecture, which is transformer, and which has become pretty successful. Although it has some problems, and I'm going to talk about that, and you can give many similar examples to that, but maybe the most radical analogy is the analogy with the Zeppelins. When people started to build them, you understood that you can actually scale them, you can make them larger and heavier, and they will become more efficient, and they can get more people on board. But then after the planes were developed, the Zeppelins were not needed anymore. It might be the same with transformers. If you look at the trends, at the research, people are trying to come up with next-gen AI. How do we get this experience that we have with the LLMs to create? How can we leverage it to create something more lightweight and quick? A couple of figures how it all works. So the super large model training is not started just like that. You use small models with 3 billion of parameters, but you need 512 cards to train any model. By the way, the scaling is reflected on the slide, but we're talking about thousands of GPUs, and you need to do a lot of experiments on the first stage to move to a larger scale training that takes months. This is where we're at right now, and there are no major alternatives. I mean, if it was easier, someone would come up with a solution. And the success stories are explained by the number of GPUs that countries were able to buy. USA, China, and Europe. We don't know the exact figures, especially for China, but I think these ones more or less reflect the reality. In the US, we're talking about 1 million GPUs in OpenAI, hundreds of thousands of GPUs in China, that's for sure, around 30,000 GPUs in Europe. That's one of the largest cluster. So for now, the more GPUs we have to get the more data, the better it works. It is a viable rule. But here we're not talking only about the hardware development. There's quite a lot of relatively small or more important algorithmic improvements. The improved optimization. Optimion became a very important improvement, and here we have Leon Sophia, of course, and many other things related to the optimization of communications, mixture of experts. All of these are architectural improvements where we still work in transformer paradigm, but we get the speed up improvements of 10-20%. If you look at the token parameterization, went down in a year by tenfold. If the cost of the token costs 10 times less, that means that we can do the inference 10 times quicker. So the algorithms are developed. If the algorithms are being developed and being sped up, why do we need all these GPUs? But this first step, meaning the 1,000 various experiments with various architecture, means that you can do more experiments. That means that it's not that you have one very costly launch where you try to train your model, but you have thousands of options on the small scale, and then you scale it to a large launch. So for now, that works like that. I mean, it would be great not to use that many GPUs, and to get some great ideas. And there are some ideas that emerge. For example, DeepSeek, that made the reasoning technologies much more affordable and boosted this story really. And that was 2025. In February, and I think it looks like it was such a long time ago, but it was just done in February 2025. So one of the areas of LLM development is scaling or hyperscaling. These are algorithmic improvements on the level of math and low-level optimizations. There's quite a lot of things to gain there, and obviously the procurement of new hardware. That's one of the areas. Does that mean that we're approaching AGI? I think absolutely not. So the story related to large pre-trains is in some way saturated. I guess we need to go back to the start of the day. There was a fantastic session related to the there was a fantastic panel. The guys were participating in contests, and right now we are on the level that we do contest winners with LLMs. They can quickly resolve problems, the solution to which is already known. You know, don't want to sound evil, but I've never participated in Olympiad contests. Olympiads and contests are very great, but you know, being a professional athlete does not mean that your people in your country will be healthier. The same with the Olympiads. These are the tasks that have been already solved and can be solved in 2 or 5 hours. And scientific problem means that there is no solution, and this is what you need to resolve. So I think this is the way, not only our way. I think that the Chinese scientists champion this way, that creating AGI means that we need to create the systems that first resolve the problems that are, first of all, very important for the humanity and for the economy, and secondly, that we don't know how to resolve. A couple of examples is healthcare, new drugs, new pharmaceuticals, designing and talking about materials. If you talk about the construction, I mean, you understand that's a daunting task. And when you get this daunting tasks and you ask ChatGPT about that, about resolving that task, they will give you a rubbish response. But what do you do about that? How did they resolve this task in healthcare?
Their solution was very simple. Let's collect all textbooks and examination questions, and let's train the models to pass exams. GigaChat was great at a medical exam for different specializations. Does this mean that such systems can be doctors? The answer is no. Why? Because these test questions have nothing to do with actual complicated practice, which is reasoning, clinical thinking, and as for the data, it's not millions of examples, but dozens, hundreds of examples, hundreds of cases. But that should be treated separately. When you are trying to solve a complicated problem, you are trying to think of ways to make an LLM into a multi-agent system. There are a lot of new emerging tools here that have to do with the fact that we need to write sophisticated code. In May this year, AlphaWolf by DeepMind published this paper, which showed that an LLM can in fact write code by itself and solve problems by itself if and only if you can check if the solution is correct. So you can ask it to solve an equation or write a difficult equation, or in the simplest case, you can ask it to write a prompt that helps you solve a specific problem. You can submit the prompt, you can start the system, get the answer, and get a benchmark metric and check if the answer is correct. Such algorithms are for the lazy people, such as myself. You simply set a task for it, you ask it to send you back an answer, you check the answer, and then you ask it to rewrite the answer again. And then there are all kinds of tricky evolutionary algorithms where the mutation algorithm is the LLM model itself. It has its experience, it has memory, a program of outcomes, it has its insights, what it came up with, and its goal is to combine those insights into new programs. First author of the paper by Revolved is Sasha Novikov. He's my postgrad student. He left the country a long time ago, but we're still in touch. And there are a lot of not less talented people at the institute. One of them is Valentin Khurkov, who analyzed it for a month and got its own result. We called it Giga Evo. With extended functionality. It's an open source model. You can check it out for yourself. Here's an example of how it works. First, practical problems, and then an example with a mathematical problem, positioning of triangles. It does happen, but there are practical cases as well. So, as I said, you can download it, you can try it. It works with any LLMs for practically any problem that you can try to improve. We use it to improve prompts, for example. We also improve regular ML models, and we improve multi-agent systems. So we give it a multi-agent system as an input, we give it a benchmark and ask it to rewrite it again and again. You just leave it for the night, you come back in the morning and see what it came up with. You can connect an open router or locally deployed inference, but still you can see on the chart that the quality of the model, the quality of the generated program grows after each generation. A huge case, we've invested a lot in it. The main goal now is to collect a large enough quantity of cases, of use cases, because once we've done that, we will see what is the uniting factor for this strategy to solving problems. Another thing that we are bringing to open source, we have been working hard on multi-agent systems, making assistants. Well, that said, everybody's making assistants. Any one of you can make an assistant, a multi-agent assistant, in 30 minutes. But what do you do when it makes a mistake? We have worked out an approach based on the Maestro framework that lets us decompose a problem. It's a methodology framework. So a problem like medical diagnosis or presentation by demand. How do we check each step? How do we optimize it? How do we implement it? It's a rather elaborate, complicated, multifunctional framework. There's a lot of other institutes can take advantage of that we would like to share with everyone. This is a detailed description of our approach related to the train of thought. The chain of thought. We decided that it will be much more useful as an open source model rather than a closed platform. We have a backbone for developing agents, and we have this evolutionary thing that can improve these multi-agent systems. We will be combining the two, meaning that our approach at the moment, our approach to the development of AGI is about, first, selecting complex problems, second, building systemic multi-agent systems that can guarantee accuracy in problem solving, and this is an intermediary step. Why? Because such systems learn, or rather not learn, but we make them solve problems well, but then they start generating a lot of synthetic data. So we are handling the problem of data deficit in difficult industries, in complex industries such as healthcare. They don't have these chain of thoughts. So a multi-agent system is an intermediary step, but without them, we will not be able to progress further. And now the rest of my presentation will be about the problems that LLMs are facing. And I would like to highlight this paper that really inspired me. This is a piece of purely academic work. The group led by Amon Shashua from Israel. He's this great guy. They showed that there are problems solved algorithmically, but at the same time, we cannot use FT or Rally or any other approaches. We cannot learn the correct solution. Very simply put, there is this repositioning of vector elements, and there are vector elements plus one, and we want to determine the target. We do not know the P, but we can have as many pairs of X8 and Y8 as we want. A simple problem, and it shows that even if you have these chains of thought that lead you to the correct answer, you will need an exponential number of these chains. The idea is simple. It can be described in layman's terms. How do we do it now? We have a problem, we have an answer. The main approach now is through chain of thought. We need to make 10 steps. We've written 20 versions of the way that we want to handle the problem, and then we train the model to predict the next step with 0.8 accuracy. So it's predicting each new step with 0.8. We take 0.8 to the power of 10, and you get the rate of accuracy with which you will progress along the chain of thought to the correct answer. But if at some point it makes a mistake, everything else collapses. In training, we do not have the rollback one step function. There is an interesting solution proposed in this article. The article is also interesting in that it doesn't have any experiments. It's a purely academic mathematical paper. An alternative approach. What if we try to think of why is it happening instead of just pumping in data? And it's true that if we were working with complex problems, we see that it generates steps in a very plausible manner, but if you give it certain freedom in terms of these steps, the rate of error, the rate of mistakes grows colossally. Another problem is lack of memory. When you open the chat, each and every time, it greets you as if for the very first time. Maybe it does retain some basic information, what's your name and the rest, but overall, when it's interacting with you, it's not learning, but it's just remembering certain episodes. If the discussion is very long, or if we want to upload a knowledge base, the problem that attention is scaled quadratically persists. At the Institute, we have a lot of interesting papers. For example, the team led by Mikhail Burtsev and now led by Yuri Kuratov, with this group, we try to come up with new architectures which do not require quadratic scaling. One of the approaches is neuro-inspired. It's associative recurrent meta-transformer. In science, when you come up with an idea, this idea starts to inspire other researchers. Titan became a solution inspired by ARMT, so it's one of the approaches that is currently gaining traction. It's very interesting. You can train a small model, but the main problem is you come up with a new idea, a new architecture. It's great. You try to scale it to the same amount of tokens, the same scalar transformers used for learning. But then it turns out you need to reinvent all the heuristics all over again that underpin this large-scale learning. And then what you do is not maths, but something closer to engineering. Another interesting paper by Yuri Kuratov, accepted in oral form at the ICL conference with a very simple idea. What we showed was we can take 1,500 tokens and we can compress them without losing any information into a single vector. The space in which language models operate is way bigger. It takes up we give it much more space than they actually need. This paper was very interesting for a lot of international researchers. For example, I visited China. I start talking about this paper, and then people start raising hands and saying, "Oh yes, we know this paper. We are already trying to borrow some ideas from it," which is why good research papers are so important, because they become a sort of a business card for you, your signature. It gives you credibility within the community. It's very important to talk about what you're doing in the form of a research paper. So compression is great, but how do you get this compression representation fast, and how do you use it for generation? Actively working on that at the moment. And this is my paper together with Gleb Mezentsev, saying that while in Kuratov's work we are taking the vector to decode token by token, here in this case we took a step further and decided that we can decode in a way that we can encode in a way that decoding will only take one forward. 64 instead of 1,500, still a compressed representation, and it allows you to work with continuous vectors rather than discrete vectors. I'm mainly talking about our own papers. Penny Lee, our PhD student, an employee of AIRI, we thought about the following problem. What if you have a maths problem without a clear solution? If you have this clear solution, you can use GRPO, you can use reinforcement learning, but it turns out that large language models can be trained even if you do not have the correct label. The idea is you ask the same question 10 times, you get the answer 10 times, 10 different answers, and the most frequent answer will probably be correct. So as Baron Munchausen, you start to pull yourself up by your own hair. So the model is training using its own answers. This drastically improves the quality of work with mathematical benchmarks and code without any labels. You can do a lot of interesting things with this. I have just 2 minutes left, and in the 2 minutes I would like to discuss other architectures. Diffusion models in text are emerging, and I really like it. Diffusion models are now at this new level where you can scale them. They have reasoning. Google has announced Gemini Fusion. They haven't published it yet for a number of reasons. But the idea is that we're not generating text using just one token, but we're trying to generate all of them, all of the portions, just in different places. The mathematics there is absolutely gorgeous. You significantly speed up inference several-fold. You go to ChatGPT, and instead of waiting for it to reason, it starts writing the answer straight away. This will drastically improve the quality of user experience. Some other ideas, many of them are available are discussed in this interview by Karpati. What we would like to see is a model that trains during inference. You ask it a question, it answers something, and it has learned something. There are examples of this. The Confidence is All You Need paper is describing precisely that. We take a model and we make it learn using its own answers. It's just that gradient learning steps during inference is very costly, so we need alternative learning methods. A lot of people are thinking about how to do it best. They try using the old Hebbian rules. It gives small changes, but still, we can draw this analogy with what we do during the day, and then we go to bed in the evening. During our sleep, our neural networks continue to learn, and then we wake up in the morning, and there you have it, some new experience. Models currently do not do that, and this is something that we want to ensure. Also, it's completely unclear what this model should look like. I can share with you my hypothesis, and there is some consensus on this. The size of the model is not the key factor. Models with trillions of parameters just a year ago are more stupid than current models with just a few million parameters or a few billion parameters. So we're talking about a model that can do reasoning, logic, has basic knowledge, and has access to search, internet, and databases. My near-future vision is that we will have a model for 20 billion parameters and then a 2 billion parameter model that can do this well, but doesn't have any excessive knowledge, because with trillions of parameters, you put in a lot of excessive information, which the model doesn't need at all for learning. And that's pretty much it. That's my presentation. I have a Telegram channel. Join it if you'd like. Thank you for your attention.